Well, long division of polynomials is very similar to long division of real numbers. And, if you divided 137 by 4, if you think back to long division, you know how you would divide that, and then you would take your remainder and you would put it over the divisor. And so 137 divided by 4 would be whatever the quotient is, which in this case is 34, and then plus 1/4. So when you long divide polynomials, you do something similar. See here, I need to figure out what would I multiply x by to get x squared. And you can see I put an x up here because x times x is going to give me x squared. Then you multiply it back, so x times x is going to give me x squared, and then x times 3 is 3x. And this is where you got to be careful. Remember, you have to subtract, just like you had to subtract 12 over here. You've got to subtract this expression from the dividend here. So when you subtract x squared from x squared, of course they cancel, but then you have 10x minus 3x, which gives me 7x, and then you have to bring down the next term, and then you do it again. X times what equals 7x? Well, that would be 7. So 7 is the next term up here, and then multiply back. 7 times x is 7x. 7 times 3 is 21. So you have 7x plus 21, and then you subtract that. Then, of course, the 7x's cancel, and you get 15 minus 21, which is negative 6. So what we can do is we can say that that polynomial divided by x plus 3 is equal to the binomial x plus 7 plus the fraction negative 6 over x plus 3. Pause the video and read these guidelines for dividing polynomials. And it's important, that everything is written in descending order, and so that when you divide, you have them in the right order. And basically, after you read this, then go ahead and play the video, and I'll show you how to do some dividing. So here's an example. It says divide this polynomial by 3x minus 2. So step 1 is to rearrange it. So I'm going to rearrange this in descending order so that the highest degree terms are first. So I get that. And then steps 2 through 4, here I'm going to divide. So I'm going to say 3x times what gives me 6x cubed. Let me get this out of the way. So divide 3x into 6x cubed, and you get 2x squared. So that's going to be the quotient. So then I multiply back. 2x squared times 3x gives me 6x cubed, and then 2x squared times minus 2 gives me minus 4x squared. But then I have to subtract, so the 6x cubes cancel. Then I have minus x squared, and then minus the minus 4x squared would be plus 4x squared. So I have minus x squared plus 4x squared is 3x squared, and then I bring down the minus 5x. Well, then I have to do it again. So now I say 3x times what is going to give me 3x squared. So that would be x. And then multiply back. X times 3x is 3x squared. And x times minus 2 is minus 2x. And then I subtract again. And the 3x squareds cancel. And then I get minus 5x plus 2x is minus 3x. And then plus 4. Well, then I have to do it again. So figure out what do I multiply 3x by to actually get, what do I multiply 3x by to get minus 3x here, and that would be negative 1, and then multiply back. Negative 1 times 3x is negative 1 times 3x is minus 3x, so that's what that should be, minus 3x, and then when you, negative 1 times negative 2 is plus 2, so that's right, and then you subtract, and the 3x's will cancel, then you'll have 4 minus 2, which is 2. So finally, you find that the result of this division is the trinomial 2x squared plus x minus 1 plus 2 over the divisor 3x minus 2. And there's a practice problem down there below if you want to do that and see if you can get the answer I got. The division algorithm says that if f of x and d of x are polynomials as long as d of x is not 0, d of x is the divisor, so you can't divide by 0. And if the degree of d of x is less than or equal to the degree of f of x, then there exist unique polynomials q of x and r of x such that f of x can be written as the divisor times the quotient plus the remainder. Okay, so that's a little tricky to follow, but let me show you what we're saying here. If you look at this example down here, this example right here, this is f of x and this is d of x. And so the degree of d of x is 1, the degree of f of x is 2, so certainly the degree of this is less than the degree of this. So if we divide that out, it actually comes out evenly. So you actually get x plus 7. So actually, as I said, this is f of x, this is d of x, this is q of x, and we didn't have a remainder here, so we'll just say the remainder is 0. So that means that we can write this polynomial as, let's say it in the right order here. You can write it as the divisor, x plus 3, times the quotient plus the remainder. Okay, now let's look at one that doesn't work exactly right. And so if you go back up to this one I did up here, where we got this result right here. So here it is, f of x, there's d of x, there's q of x, and then there's r of x. That's the remainder. Okay, so basically that we're saying we can write this polynomial using that theorem as the divisor times the quotient plus that remainder. So that's basically all that division algorithm tells us. Okay, so in order to divide using synthetic division, first of all, again, write your polynomial in descending order, and then use a 0 coefficient for any missing terms. So let's say I want to divide x minus 3 into this polynomial. Well, notice there's no missing terms because you got degree 3, degree 2, degree 1, degree 0 for the constant. And everything's written in descending order. Okay, so let's talk about, to do synthetic division, it's only when you're dividing by x plus or minus a constant. So if it's x minus a constant, you're going to use the positive constant. If it's x plus the constant, you're going to use the negative constant in synthetic division. So since we're dividing by x minus 3, we're going to use plus 3 here, out here to this side. And then we're just going to write the coefficients of these. So the coefficients are 1, 4, negative 5, and 5. And then what we do is we write the leading coefficient here on the bottom row. Okay? And then what we do from there, there's just a pattern you follow. You're going to take this divisor 3 and multiply it by this coefficient. So 3 times 1 is 3, and we're going to write that result under the next term right here. All right. Then we're going to add. We're going to add these two numbers together. So it's a little different than long division. We're adding these. So we take 4 plus 3, and we get 7. Well, then we do it again. We multiply 3 times 7, and we're going to get 21, and we're going to put 21 under the next term. So 3 times 7 gives me 21 here, and then we add these terms together, and we get 16. And then we take 3 times 16, which is 48, and we put that there, and then we add these terms together, and we get 53. So basically now, what we find out is the first 3 terms here is the quotient. But we have to reduce the degree by 1. So we started up here with a degree of 3, so the quotient has to be a degree of 2. So that would be 1x squared plus 7x plus 16. And then the last term is the remainder. So finally, we know that our answer is the result of that division would be x squared plus 7x plus 16 plus the remainder over the divisor, 53 over x minus 3. Now we can do this a little quicker than what I did the first one. So here I'm going to divide by x plus 2. So I'm going to put negative 2 here. And then I have 5x cubed. I have no x squared, so I'm going to put a 0 for the squared term. I have 6 for the x term and then 8 for the constant. And then over here, I'm going to bring down the 5 and put it right here. Then I'm going to multiply these together and get negative 10 and put it under the 0. And then add 0 to negative 10, get negative 10. Then multiply again, negative 2 times negative 10, and you get 20. And then you put the 20 under the 6. And then you add these together, and then you multiply again. Negative 2 times 26 is negative 52. And then you put the negative 52 here, and you add these together and get negative 44. And since the degree was of the dividend was 3, now the degree of the quotient will be 2. So this will be 5x squared minus 10x plus 26, and then minus 44 over x plus 2. And that's your answer. Now, I'll let you do the next one on your own, but let me just remind you, if this last sum here is 0, then that just tells you the remainder is 0, so the answer would just be this quotient that you get. In this case, it would be x squared plus 4x plus 3. So that's how you do synthetic division. The remainder theorem basically says if you divide the polynomial f of x by x minus c, then the remainder, just the number part, not the divisor, is f of c. Well, let's go back and look at one we just did. So notice when I did this one and I divided this polynomial by x plus 2, notice the remainder turned out to be negative 44. So let's see what happens here. If you evaluate this function here at, let's evaluate this function at negative 2. So remember, we got to take the opposite sign. So since it was x plus 2, we're going to divide by we're going to evaluate it at negative 2. So if you plug negative 2 back into this function, you're going to get 5 times negative 8, which is negative 40, plus 6 times negative 2, which is negative 12, plus 8. So you're going to get negative 40 plus negative 12, negative 52 plus 8 is negative 44. See? So you do get that remainder value. Okay? So now, if I wanted to find the remainder, we can find f of 2 by actually doing synthetic division. I know this is the long way, but we're going to prove a point this way. Okay, so what I'm going to do is I'm going to take this and I'm going to divide it by x minus this number, x minus 2. And so if I'm going to divide it by x minus 2, then I'm going to be basically using 2 here. So now do synthetic division, bring down the 1, 2 times 1 is 2, put it here, add it, get negative 2, multiply again, you get negative 4, add it to 5, you get 1, multiply again, you get 2, add it to 3, you get 5. So the remainder is 5. Now, check f of 2, and notice if you plug 2 into that function, you'll get 5. So pretty neat, huh? Now, do the same thing for f of negative 4. Actually, freeze the video and you do this example, then you can check it over here just like I did. So let me move on to the factor theorem. The factor theorem just says if f of c is equal to 0, then x minus c is a factor. So basically, it goes both ways as well. If x minus c is a factor of f of x, then f of c is 0. So if you take this polynomial, and if you evaluate this polynomial at 3, you're going to see that you're going to get 0. So what that tells me is that x minus 3 is a factor. Okay. Here, if you show that f of negative 3 is 0, then you know x plus 3 is a factor, so x plus 3 is a factor, so f of negative 3 should be 0. And so we can easily show that x equal to negative 1 is a root of this by evaluating this at negative 1. If you evaluate negative 1 at this, you're going to get 0, so f of negative 1 is a root of f of x. So x equal to negative 1 is a root. So once you know the root of a polynomial, like here, if we show that negative 1 is a root, we can actually get it reduced to a smaller polynomial or a smaller factor, and then from there we could actually maybe solve the rest of it by factoring the quadratic. So take a look at that and see what you think. I got to move on.